see. Okay. A little bit on the motivation. So we have here the global temperature profiles in the ocean since 1960. And we have the temperature profile. We know that they are historically the most common observations we have about the ocean. And historically, we have here several different platforms, and we know that they change over time, the density of this platform. And we started in 1960s, with most of the data was collected by mechanical bathythermograph, up to more than 70%. And then after the 60s, especially in the 70s, was the XBT profiles that they started dominating the ocean and basically collecting temperature data worldwide. And later on, where we have the profile floats, the algal float start to increase for global ocean temperature. We see that the XBTs starts decline, so we wouldn't need XBT more to investigate global ocean heat or temperature. And we also have at some point like the pinnipads. The pinnipads or the mammal CTDs, they especially for the Southern Ocean, and also peaked at a certain point. And for this, thanks to these the temperature observations, we are able to draw like what the ocean heat content and the ocean heat uptake is doing since the 1960s for different basins. And this is and it's Li-Jing Cheng who has been working very deeply on that lately, on correcting the XBT data and etc. And so this is used, for example, for ocean heat content, also for the thermospheric sea level, how much the temperature influence the sea level rise over the decades. And we see that this decrease in the XBT, that is mostly because now the project starts, the XBT network starts focusing more on ocean currents and key processes instead of globally, but it still have a pretty good global coverage. And you see that's for temperature, but you see for the salinity, the story is a little bit different, right? We have, for example, this paper by Shang et al. 2011, and we have here comparing the yearly global observation for 1993 and 2008 after the Argo picked up. And we have for in green for all the profiles that we have temperature and salinity together, and in red the temperature only. And we see that salinity in the 90s was still not very, with a bad coverage, especially in the southern hemisphere, the whole southern hemisphere. And nowadays we have a coverage, and it brings the idea of how can we overcome this lack of observation, especially on the time. And so several studies came with this idea of inferring salinity from temperature profiles. So we know that the TS relationship is generally conserved in most of the ocean, and so they draw like statistical relationships to infer salinity at several places. But generally, like this one, they are from TACA 2007. So this is one we use the most here, for example, at the AOML to estimate ocean currents and heat transport and everything, MOC. And it's generally like that. So it generally like regionally based. So this one was from 25 south to 45 south. And this on 2007, where we had very little Argo data at that time. So we had this is the density of the data we have. We are lucky where we had like 50 profiles within a grid point. And this paper by Tucker especially pointed out how the salinity is related to the square of the temperature in the ocean. So, and it's very successful to analyze this squared relationship and very successful in get most of the salinity variability. So for this study, what we want to do is use the updated hydrographic data, which for example, Carlisle didn't have in 2007, and to infer like this salinity relationship in an updated manner and try to infer some of the interannual variability or what we can't capture or what we can capture with this relationship. So the outline here, first I will talk about the data and the spatial domain. So this will be mostly in the Atlantic domain, as we'll see, where we do most of our work. And I'll present here 4 different methods. And 2 of them are based on regression with the R here in the front that I'll talk a little bit later. So these are more sophisticated than the other 2. And I'll do some analysis of residuals and the impact of the MOC or heat transport and freshwater transport along 34.5 south, which is we have several places like Shenfu and others that are very successful on doing that. Some conclusions and future work as well. So first I'll talk about the data used. So this is the total population, use the trial population. So this is used to calibrate the regression models I'm going to present. So we use 2 types of data, the non-Argo, so and the Argo data. So from in both of them together is about 1 million profiles in the whole Atlantic between 75 south and 65 north. And for the non-Argo data, this comes from the profile data from the Quora 3.4 data set with a Coriolis data set they put available in France since 1990 to 2011. So this one stopped in 2011. And it takes into account all the CTD, XCTD, underwater gliders, mooring, pinnipedes, and also Argo. So for this one, I got rid of the Argo data. And for this one, the Argo come from the NODC dataset, so it can be downloaded on the web from 2012 to 2015. And this is more or less the distribution of the data. We see that the non-Argo is mostly through different transects over time, and a lot of them along the boundaries where we have a more sampling historically, and the Argo, of course, is more larger coverage and several regions with above 300 profiles per degree squared. And all this data is interpolated at 85 depth levels from 7.5 meters to 2,000 meters. And if you look for the validation, so after we calibrate the regression models, we do a validation data set. And so this is the same figure here, but for the validation, we use Argo 2016, as well as the AX18 data set. So this is the high density XBT around 34 south. So this is just a DynH sensitivity. And this is about 51,000 profiles for 2016 and 61 transects. And when we analyze the time evolution of the residuals, so what we do is divide this whole data set that we have initially in half. So we use half for calibration and half for verification. And we divide the main domain in 5 subbasins. So it would be the Southern Ocean, South Atlantic with north of 45 south, Tropical Atlantic from 15 south to 10 north, North Atlantic all to 45 north, and then after that is called the Northern Ocean, but is like subpolar region. So the method, so as I said, we are going to apply 4 methods here. The first 2 methods, they are more for historic reasons. So these are the classic methods they use to infer salinity in the ocean. The first one was devised by Stommel in 1947. So this basically, which shows that the main TS relationship can be very, very strong to infer the salinity. So we just use the mean TS relationship, and we have when you get a new TS, a new temperature profile, we interpolate linearly and get the salinity at that profile. So this is good, but when you, as we see later, when you have a water column that is too homogeneous in salinity, like the method basically gets lost with the interpolation. And the other is the salinity mean, that's the Emery and Dewar. And what they want to say is that, exactly in the region where the water is too homogeneous, we can use just the mean salinity profile. And this would be better than the mean TS instead. And the other 2 methods, they're based on a regression method, linear regression method. And it's called the RDIST, with a regression with distance. So this is the method used by Tucker in 2007, which said that salinity at each depth is related to temperature squared, and the distance with latitude and longitude to the center of each grid. So these are the predictors here, TT squared, lat, and lon. And the RSEAS, and this is the method we tested during this work, where instead of RDIST, instead of lat and lon, we replaced that by the first 2 harmonics, the annual and the semi-annual harmonics. So the C is for seasonality. So we tried to see what by representing the seasonality, the annual and semi-annual harmonics, what gain we would have. And this came partly from the ideas, I guess, from Rick's talks that talk about seasonality in the drifter data, and this is something that came partially from that. And this, after that, we need a mapping. So what we do for the whole basin, we divide the 1 by 1 degree beans, and these beans would have at least a minimum of 150 profiles. And if they don't have in this 1 by 1 degree bean, we can search in a larger region for each of the degree bean up to 4 degrees. So if we want to do in this 1 degree here, we can search up to a 4 degrees range for all the 150 profiles that we have nearby. And with that, we use a weighting function for the mapping that is just a square exponential. Is basically a Gaussian that is centered here in the middle. And as you go further, you have less weight for the data. And this is what you get in degrees. So from 1 to here is to 3.5 degrees. What is the search area for each of the grid points? And we see that mostly in the Atlantic is basically 1 by 1. So we have enough data to do the regression at each point. And we have some regions, for example, the Caribbean Sea, the Southern Ocean, and here in close to the Patagonia Shelf, that generally don't have enough data. So it searched for a larger region to do.
Did you code it up so it wouldn't search on the other side of the Panama Canal, for example?
No, I stopped there. As I stopped in this work, I also stopped for the Mediterranean, because the Mediterranean was really impacting, because it's so high the salinity there that is really impacting if I do a search around there. So Mediterranean, it's one by itself, but it's not analyzed here. It's one. So this is just some sample profiles. So I select one profile for each of the basins. So this Northern Ocean, North Atlantic, South Atlantic, and Southern Ocean. One typical profile, and see how for the Argo 2016, which is in black. I hope you guys can see. It's probably under the other lines mostly. But it's the Argo we compared with the S mean in blue, the TS mean, the mean TS, and the regression RDIST and RSEAS in orange. And you see that for the Northern Ocean, we see it starts with the S mean, with the mean salinity. We have that the mean salinity, and it happens in several of the basins. It can't conserve. So this is the TS curve. So this salinity and temperature, and this is depth and salinity. So this salinity profile is a TS curve on the top. And we see that for the Northern Ocean, we see that the blue curve, the S mean, in this region here, you can get partly the profile, but some of in these regions where we have a strong TS relationship, strong linear TS relationship, it just doesn't conserve the TS relationship where you have a strong linear. And this is generally captured by, if you apply the TS mean, so that would conserve the TS in most of the cases. So with the TS mean, just using the TS, you have a problem in region where you have a stronger nonlinear relationship between the T and S. It's very good where you have a linear relationship, and it fails, for example, in the South Atlantic and South Atlantic here, where you have the Antarctic intermediate water. It just fails completely because it gets lost in the interpolation. And the same when you have a strong homogeneous profile as in the Southern Ocean. And the two regression methods, the RDIST and RSEAS, they're very, very similar in this point. We have this, generally the RSEAS, when you added the seasonality, it improves a little bit at the surface of the profiles relative to the Argo, to the black curve, and relative to the red when you use the distance. So, but so far they're pretty similar. And if you look at now, not a single profile, but the basin average of these residuals for the 5 basins. So this is salinity over depth. So this is average over 4 different level range from 0 to 200 meters, 200 to 800 to 1200 meters and 2000 meters. And we see by comparing the methods as well. So we get exactly the same response as for the single profile. We have that the TS mean, it has very difficult time in getting the waters where it's too homogeneous, like in the Southern Ocean, and in the regions where you have the Antarctic intermediate water. And the S mean, we have especially here at the mid depth, where we have a stronger linear relationship. It can't get, so most of the areas where you have a stronger, especially in the central water, we have a linear relationship, it can't get, and also strong values at the surface. And the RDIST and RSEAS, the regression methods, they are pretty similar below 200 meters. And at the surface, we have that by including seasonality, it gains a little bit, about 0.02 in the whole basin. This is the maximum range of uncertainty. So this is 90% confidence interval. So it generally gains a little bit at the surface in general for the whole basin. And if you analyze in terms of dynamic height compared to 500 meters, and also the response is similar. We see that for the regression methods, in all the basins, it's mostly constrained between 5 centimeters of dynamic height uncertainty, just due to this salinity inference in comparison to the Argo 2016. And you have in the Southern Ocean really strong up to 20 centimeters uncertainty if we use the TS relationship. And in certain regions, you have that the mean salinity can drive a lot of uncertainty, for example, in the tropical and South Atlantic. So if we look, try to look at the errors for the whole basin, this is again that picture of the degrees, the range of degrees that explains how much data you have regionally. And this, if you calculate the RMS error in PSU for the salinity, for the RCs, when you include the seasonality, we see that most of the errors are below 0.05 PSU. And we have the regions, of course, the regions of strong variability, such as the Gulf Stream and the North Brazil Current. And so these regions is where you get most of the uncertainty. And if you account for just the variance explained by just the harmonics in comparison to the total variance, and we see where the harmonics could be important relative to the RDIST. And we see, and it's mostly in the fronts like the Gulf Stream and the Brazil Malvinas, and here in the Caribbean region. So all this region with the strong variability, also where the harmonics can be very effective in explaining the salinity variability. And if you do a ratio between by including seasonality or the distance, so if you get the ratio of the RMS, and we plot it here, so if the ratio is 1, it means that you have the same uncertainty for both. If it's below 1, it means that RCs, the RMS is smaller. So we see that most of the basin, including seasonality, we gain a little bit, some incremental gain over the basin. Of course, in the regions with the low coverage, because we are now in the RCs, for example, we have 4 more parameters instead of 2 more parameters, which is lat long. So in the region with the low coverage, we generally have higher. We don't have too much gain. If you look at the time evolution of the salinity residue, so what here we did is get for each of the basin, we do a monthly average of all the profiles within that basin and plot it over time. Since 2000, because before 2000, there's much more scarce data. So from 2000 to 2015 in the x-axis, and here's depth from 0 to 500 meters. And on the top here is just for the regression methods, is the average of the salinity residues, just in the top 150 meters, which is very near the surface here, where we have more influence of the seasonality. So what we can see is that I'm not going into detail here to the whole figure, a lot of panels here, and I'll just see that of the TS mean, when you have the mean TS in the Southern Ocean, as we saw before, has a strong salinity bias. And the salinity bias is not seen in the other methods, the mean salinity and the regression methods. We see that, and in the North Atlantic and Northern Ocean, you have a stronger compensation here for the TS mean. And this is, again, where we have a strong variability. And this we can see also some trend here, which may be just driven by the shift in the temperature and not really by salinity. So it captures that trend. And also you have for the RDIST and RCs, so we have the the RCs by including seasonality, you see, can you see these wiggles here in most of the residuals? And this is because there's still seasonality of the residuals that is not captured just by linking temperature and salinity. And when you include seasonality, this is mostly gone. And we also see like some strong interannual variability here, especially in the top 150 meters that I'm going to explain you a little bit better. And here, just focusing in the regression methods that are the best two ones. And we see in the top 150 meters here, if you do this average, we have, this is the North Atlantic and Northern Ocean. We have pretty much the same pattern, very similar pattern in the two. So it may be linked to large scale process. And just a simple comparison with for the Northern Ocean, this time series here, with the NAO, we see especially at the beginning, good relationship and at the end, but it's hard to see just from a correlation. So this needs to be better investigated. So the effect of these large scales in the evaporation and precipitation. And again, we see in the RDIST, when you include just the distance, we see these wiggles of the seasonality that are most gone in this other profile. So just look quickly at the residual autocorrelation for when you include seasonality or not. And we see that in the autocorrelation of the residuals is really, you see that 12-month peak that includes the seasonality that we can't capture by the method. And when you include seasonality, that's gone. So we have and again, from including seasonality. And this is the last part here where we try to look into the sensitivity of the AMOC, meridional heat transport, freshwater transport. This is across 34 South. This is along the X18. We have this transect since 2002. And in a recent paper here by Shenfu, she used, for example, the altimetry to derive temperature profiles, and that with the help of the estimated salinity, we can estimate all this meridional heat transport, AMOC, and freshwater transport across this section. And so in a earlier paper in 2015, I analyzed within a model what would be the effect of the padding. So because we need some approximations to use the XPTs that just measure temperature in the top 800 meters to include the whole basin. So we needed a padding of temperature and salinity below 800 meters, the TS lookup table in the top at 800 meters, and then we compare with them with the two approximations. And these are against the residuals against the model with no approximation. And I'll just go quickly here and just show that depending if we don't get the seasonality, we can have a seasonal signal in the residue of the AMOC and meridional heat transport, and that is due by the lookup in blue. And when you add the padding at the lookup table, and we see that residual variability. So if you look at the X18, what would be the residue of the 61 sections that we use in terms of salinity and velocity along the section so this is longitude and this is depth. So this, because we don't have a salinity to be as like the original or the observed salinity, we use the RSEAS method that we see that we believe is the better one, and calculate these residues, the other methods minus the RSEAS, the S mean minus the RSEAS, and the TS means minus the RSEAS for salinity and velocity, derived velocity along the section. And we see that, again, the regression methods, they are generally the salinity errors are very close to zero, below 100 meters. This is most of the error can go up to 0.2 in the western boundary. where you have especially where the RCs get some good relationship where you're seeing the RMS ratio. But it's mostly in the top 100 meters. Below that is very little, and the velocity errors are around 0.02 meters per second. And the S mean error is much bigger and goes all the way to 800 meters. So this is because this is a region where we have a strong TS relationship, and there are the S mean doesn't get this this relationship with the TS, yeah, and then the velocity, we hear for this one, the velocity is even like 4 times bigger the range from the others because it's much higher. So the S mean really gets most of the error because it can capture this compensation between temperature and salinity, especially in the boundaries in the east and the western boundary. And for the TS mean, we have here mostly in the surface the TS breaks, most near 200 meters. So if you look at the time series, I just show quickly what you see, and for that S mean that creates that most of that error in velocity and salinity, and this we analyze the time series since 2002 to 2018 for meridional heat transport and freshwater transport. We calculate out for the AMOC, but it didn't plot here. We want to see that by including just the mean salinity, we can have reversions of the meridional heat transport below zero here that we don't see with other reconstructions. And for the freshwater transport, because it's the inverse of the salinity, is basically the opposite of these variabilities. Is more northward than it should, and the others they're pretty much on the top of each other. So we see that salinity doesn't really drive too much of the variability. And here, looking at the climatology, we see that the climatology also for the just using the mean salinity is the variability is much higher in the climatology because that compensation between salinity and temperature it tends to reduce the variability of the seasonal cycle here. But not too much. Yeah, for the freshwater transport, we thought it would be more sensitive because we use salinity directly, but it seemed that not too much. And this is the difference between the relative to the RCs, and we see also some effect of the seasonality, but it's generally pretty small for the regression methods. They're pretty similar, and the difference is below 5%. And so just the conclusion here. So you see that including seasonal information for salinity estimates can improve the salinity, especially in the top 150 meters of the ocean. So we see some interrenal to decadal residual variability that we still can solve, even though we can solve the seasonality, but there's still this variability. So that's unrelated to temperature. And this may be driven, as you see, for large scale processes, as well as ocean advection that we don't account here. But then there's a small, on average, is 0.21 PSU. And so just using the mean salinity is not recommended for the AMOC studies. And the regression methods, the difference between the two is below 5%. So we believe that both Tucker method and the RSEAS method, they can have robust estimates of that. And for the dynamic height, most of the regression methods is mostly below 5 centimeters. And the applications, so direct applications we have for this is that we can use for the XBT and altimetry reconstructions, for the AMOC and boundary currents and all the studies we do here with XBTs. And this is already been used. can be used operationally. So that's why also we didn't include too many predictors, because you want to be quick with the information we have from a profile. So this is the best we could do with the information we have in hands. And also can use in a simulation. For example, if we have temperature profiles only, we can create a salinity profile and use both. And some work show that if you include both, you improve your simulation relative if you just put just temperature. And there is some of our colleagues in Brazil are really interested in using that in their simulation procedure there. And for future work, so we can easily expand for the Pacific and Indian Ocean, so that would be a global product, and we can use it to investigate also decadal and interannal variability. And this is mostly done right now. So this since the publication. So I'll show you one slide in the end. And so what you can see is improving our weighting function, our mapping. So recent works show that the mapping is really important for a global reconstruction, for example, ocean heat content and things like that. So we can also have a depth correlation, because right now the correlations are at each different depth, one regression for each depth. So use some SVD or EOF methods, and or use observational errors as well. So ideally, we should have a NetCDF output. This is in MATLAB, but with NetCDF output, you can just upload the region we are interested in. That could be improving the speed of the method. And one thing that I've been talking to Lijin Cheng in China, so he's been very interested in using this to calculate the halosteric sea level changes since 1960. And as I said, the mapping is really important for this, and this could we could use this method to as at least a first approximation for the salinity, and would improve the halosteric contribution for sea level. And so for this, we could use, for example, precipitation and evaporation as other predictors for that. So that would improve the interannal variability as well. So this is once you have this working, this could be the next step. And here, just what we've been doing is, so I managed to get other profiles now for the Pacific Ocean, non-Argo and Argo as well, and for the Indian Ocean. And now we can have like global estimates of, this is the degree, this is the searching range for each 1 degree, and this is the RMS error from the estimate of salinity we see. And now we see all the boundary currents and the equatorial region, all the regions that are with the strong variability. And I guess that, yeah, and also on the SVD method, so the SVD in compared to RSEAS, so we use the SVD that take into account the whole column. So we use correlations with depth as well. But it seems that it also suffers from that seasonal variability, that you really need to explain that seasonality, even if you capture better the range over depth. This is for the Indian or the tropical Indian Ocean with the new data. So thank you.